So, welcome back. Our next speaker is Mattia D'Antonio from CINECA. He's going to talk about integration of iRODS data workflows in an extensible HTTP REST API framework.
Good morning to everybody. I'm Mattia D'Antonio and I work in CINECA, the Italian Supercomputing Center. CINECA is involved in many European projects and national initiatives, but for what concerns my specific group, CINECA is involved in many data management projects, so a huge number of data-driven projects. Of course, every project has its own very specific requirements based on the different scientific context, based on the different project. But by analyzing all these requirements, usually, often, always, a list of common needs can be identified. And this is why we are building a common layer, in particular for data management, but also to create services built on the data level to share solutions among all the projects on which we are involved. And iRODS has been adapted as the base technology for all these projects because iRODS allowed us to achieve many of the requirements, of the common requirements of these projects. I will give you a very brief background about these projects to be able to highlight what I mean for common requirements. So I will introduce some key concepts from these projects. The first use case is the UDAT Collaborative Data Infrastructure, the CDI. CDI is a network of nodes that provide several data management services for upload, retrieval, identification, replication, transfer of data, generically data. And nodes are essentially data centers like CINECA. In particular, CINECA is involved in two different UDAT services, two core services. The B2Safe, that is a data and policy management service built over iRODS, and B2Stage, that is an HTTP API interface built over B2Safe. So there is iRODS, B2Safe, B2Stage. B2Stage is a RESTful interface that offer functionalities for easy data transfer between UDAT resources, typically B2Safe and so iRODS, and external computational facilities. The main requirements of this project is the opportunity to access to data from an HTTP interface, so in a standardized way, and the flexibility of this project to be able to be integrated with other UDAT services, and the ability to be extended to be used as a base for other projects. And this is exactly what we done with the second use case, that is CData Cloud. CData Cloud is a pan-European infrastructure for ocean and marine data management. So not a general purpose data management project like B2Stage, but a specific project tailored on oceanographic data. CData Cloud is a network of sensors, ships, vessels, platforms across all the seas around Europe, but also around the world, and collecting information about physical data, chemical data, biological data that all are collected into a centralized repository to be standardized, validated, and indexed. CData Cloud components can be divided into three main categories. So there is a set of HTTP APIs, basically synchronous operations built over B2 stage, used to ingest data from the sensor networks and to be able to retrieve these informations. There are a second component that is a set of asynchronous operation that we implemented to perform whole heavy data management tasks. And we introduced an asynchronous task management framework that is Celery. And the third component is an environment used into the project to be able to execute quality checks on the ingested data. Quality checks are performed by executing Docker containers, and the execution of these containers is integrated into the APIs that we developed for the CData Cloud CDI interface. The third use case is a genomic repository that we implemented in collaboration with the Teleton Foundation, that is an Italian non-profit organization for genetic disease research, and SIGU, the Italian Society for Human Genomics. So we are totally switching the scientific context from oceanography to genomics. A genomic repository is a platform on which a researcher can deposit sequencing files. A sequencing file is basically an ASCII file produced by next-generation sequencing platforms that are machines able to read DNA and RNA and produce as output the exact list of nucleotides observed from the biological material. So it is able to convert biological material to digital information. The platform has to manage metadata and annotations on the files, create correlations between datasets, but a very important requirement for this project is the ability to execute high-performance computing analysis, bioinformatics for flows, on the input data. This is because the input data is raw information, not human readable, and analyses are required to extract meaningful information that have to be included in the repository to create correlations in the network of information. So I don't want to go more in deep on the projects with small requirements, because of course this is out of topic, but I simply want to give you an overview of the different projects on which we are working and why we are producing this shared framework. This is some of the very high-level requirements that the framework is aimed to achieve. Of course, the most obvious one, a facility for data storing generically. So all of this use case need all the data management layer. Management of metadata, most of the projects require it, in particular all the more scientifically focused projects. The access through REST APIs, all projects require this. The execution of asynchronous operation, for example, all the data-intensive tasks on CData Cloud or all the parsing activities on the genomic repository, and the opportunity to share the information inside the archive, the repository, on high-performance computing clusters or other workflow managers, so the ability to use the data on different environments. So we created this common framework named Rapido to share solution among all these projects. Rapido is a short name for REST APIs with Python on Docker. And basically can be described by two point of view. First of all, it implements a set of REST APIs integrated with several services, and in particular iRODS, and implement whole core endpoints, for example, for the authentication, all core endpoints that are used by the project based on this framework, and that can be extended by including specific endpoints. But Rapido is also built as a wrapper of Docker Compose. Docker Compose is a software that extends Docker. Docker is a lightweighted virtualization platform that is used to execute single application and all the context, library, operating system required to execute the single application in a very insulated environment. Docker Compose is a tool able to create a network of these containers. And Rapido is built as a wrapper for Docker Compose. And it is able to merge together different levels of configurations at general level, configuration at project level, and configuration at deployment level. So different level of configuration to create dynamic Docker Compose configuration for an easy deployment on every platform, from the home laptop for development purpose to the final production server in a very easy way. So this is the main stack. So we have Docker, Docker Compose, and the Rapido controller. Then all the services that can be deployed through this framework. So databases, task management, software auxiliary, of course iRODS that can be executed in a Docker container, or of course as a whole other resources can be configured as an external resources. And on top of this services layer, there is a Flask server implementing HTTP APIs with the core endpoints and the project endpoints. On top of all the stack, there is an Nginx proxy introduced for security reason, but also to introduce features, for example, the SSL certificate management. Well, now let's go to the main topic of this talk. HTTP APIs are written in Python, in particular by using the Flask micro framework, and iRODS officially support Python through the Python iRODS client. But to make easier to interact with iRODS and with the Python iRODS client, we created a wrapper client that implements a set of common operations, and this client is used from both the API endpoints and the asynchronous tasks. The methods that we implemented into this client can be divided into three main categories. There are a number of methods that can be mapped on corresponding high commands. For example, methods for list, make dir, put, get, move, remove, set permissions, ticket, that clearly can be mapped on corresponding high commands like ILS, IMakeDir, and so on. Most of these methods are directly mapped on Python iRODS client features. For example, the makeDir method is simply mapped on the analogous method on the Python iRODS client, but by adding checks and catches of exceptions, for example, for permission denied, collection does not exist. The basic idea is that Python iRODS client usually forward the exception raised from iRODS, and this exception is not usually human readable for the final user. So what these wrapping methods do is to catch the exception, parse it, modify in a human readable exception, and then true again. So are simply utilities. A second categories are a set of methods that cannot be directly mapped on a commands. So are very simple utilities, like methods to verify if a path exists on iRODS, if a path corresponds to a collection or to a data object. The third category is a set of more complex operations, typically a set of input-output methods to read or write content of data object. Data object can be read as a string, can be write by passing a string, so direct read and write, but can also read and write in chunks, so by passing an iterator, or directly by streaming information from Flask. So this is the typical use case when integrating HTTP APIs on web interfaces for upload or to download files. So in this case, for the upload, the data is directly streamed from the browser or the client through the HTTP API directly on iRODS. And this is a much more efficient way to upload or download these files. HTTP APIs support all iRODS authentication protocols, so native credentials, PAM module, GSI. Python iRODS client natively supported native credentials, so in this case the integration on Python level has been very easy. But PAM and GSI was not supported originally from Python iRODS client, and so we decided to contribute to the development of PRC by, we love open source, by implementing the support for both GSI and PAM. GSI is considered to be a completed task, and the GSI module has been merged on the main branch in January 2017, and it is considered to be completed. The PAM module has been merged on the main branch in December 2018, and it works for some use cases. Now we are working with PAM module on the projects that I presented, but we know that there are some issues with some other use cases, so some fixes is still required to accomplish this integration. Well, we are working on it. I already introduced the asynchronous operations layer that we built with Celery. What is important here is that all the functions, all the utilities, all the services integration implemented in Rapido are shared between the different components of the framework. So every operation that can be executed in a synchronous way from the API endpoints can be implemented exactly in the same way on the asynchronous context. So a typical use case is to start to implement a feature directly on an endpoint in a synchronous way, because it is simpler, because the data are smaller. Then it becomes evident that the synchronous way does not work. It is required to make it asynchronous. And it is quite easy to simply migrate the code from the synchronous environment to the asynchronous, from endpoint to Celery. This means that Celery is able to interact with iRODS in the same way the endpoints do. We know that many projects need to store data for archiving purpose and use data simply as read-only resources. But many other projects require to use the project as input, for example, for analysis, to modify these files, to produce more information. And the use of iRODS ensure to accomplish very, very easily this task. because with iRODS it is possible to access to data from many different locations with many different clients. So it is very easy to ingest data from HTTP APIs and then access to data from the high-performance computing clusters. What is very important for some projects, for example, for the genomic repository that is storing clinical human data, so very, very sensible information. What is very important is the security level. And with iRODS, also by modifying the client user to access to data, Python client or iCommands from APIs or from the cluster, we know that the security level is fully preserved, and all the access control lists, the ACL, set for the data are fully preserved. So this is a very important requirement for us. This is the simply workflow that can be implemented. Thank you to iRODS, very, very simple way. Of course, APC clusters are not always the best solution because for some projects, some more flexibility is required, and this flexibility can be achieved by using Docker. And Docker containers can be automatically orchestrated by using services like Rancher. Rancher is a container orchestrating platforms that offers many clients, web interface, a command line interface, and a REST APIs interface. And Rapido implement a Rancher client integrated on both endpoints and asynchronous environment level to be able to interact automatically with Rancher to create Docker containers. So it is possible to create data workflows by creating a Docker environment, mounting resources, configuring the containers to access to iRODS, and so create a very similar workflow, similar to the APC use case, by using a virtual environment. So from APIs through Rancher, create Docker. Docker can read and write on Docker, and then ingest results on APIs. So why we are so happy to use iRODS? The use of iRODS allowed us to achieve several requirements of the projects on which we are involved. First of all, the stability and scalability, also for big data projects like for genomics and oceanography. The accessibility from different locations, REST APIs, APC clusters, the preservation of security and access policies, the number of authentication methods, because some of our projects are certificate-based, some others are defined on LDAP servers, so we can switch between GSI, PAM, and so accomplish whole authentication that are required. The opportunity for easy data replication, for example, the CData Cloud archive is automatically replicated across different centers in the UDAT network. So thank you to iRODS, it is easy. And the opportunity to create rules to automatize a number of workflows. Just to conclude, iRODS is the perfect technology for these projects, but iRODS itself is not enough for all the requirements of the projects. A number of higher level services are required and have to be built over iRODS. And since many projects have common requirements can be translated in common solutions. So usually there is no need to reinvent the wheel. So we can reuse best practices and solutions already implemented on previous projects. But of course, this approach has the huge risk to continue to use solutions that can become obsolete. So there is the risk of fossilization. And this is why every project has to use all the previous project knowledge, but by improve it. So Don't reinvent the wheel, but perfect it. Well, thank you. Of course, Rapido is an open source project that is freely available on GitHub. If someone of you want to have a look, you're welcome.
Thank you. Do we have any questions? Did you make up the name, Rapido?
Yeah,
It's a good name.
Rapido.
All right, thank you so much.
Thank you to everybody.